hashing competition. So last year I presented actually the Catena framework, and today I want to present variants of this framework. So we worked on it and we find some new instantiations for the underlying primitives, and so now I want to present how far we got. So yeah, I want to do some motivation at the beginning, then I want to introduce the Catena framework itself again, because some of you might not know it so far. Then I want to present some extensions, some basic graph structures which we use to instantiate the core of Catena. Then I want to talk about the hash functions which we consider, but this is just a briefly comparison. And then at the end, the most important part is I want to present 4 new recommendations which we found so far, which we constructed based on our requirements. So first of all, okay, password hashing competition, sorry. One during 2 years, from 2013 to 15, or 3 years, where at the end the winner Argon was chosen with 3 different variants. The first one is Argon 2i, which is has an independent memory access pattern, which means it is not vulnerable against cache timing attacks, for example. Then there was the second variant, Argon 2d, which has a password-dependent access pattern, which is then has resistance against ASICs, for example, or FPGAs or GPUs. So it's a quite nice trade-off resistance. And then a mixed or hybrid variant, Argon 2di. And today I want to present similar variants to the winner, but which were built using our framework Catena, which was one of the 4 PHC special recognitions alongside of Lyra2, Marqua, and YesScript. So during the password hashing competition, there were a lot of new ideas, like we had to consider memory hardness because we want to be resistant against FPGAs and GPUs, because we always want to exploit the slow memory. So we do not want to have the memory when you hash one password just in the level 1 cache, so we want to go far beyond that. So we want to say, okay, we want to have like 4 megabyte, 64 megabyte, or even 1 gigabyte of memory to exploit these kind of attacks. Then we introduced actually the garbage collector attacks, which only work similar for the cache timing attacks if the adversary has access to the PC where the password is actually hashed. And the garbage collector attack just looks for the memory, which is for the state words of the password hashing scheme, which are in the memory after the password is already hashed, and then we try to find a faster way to compute password hashes to test candidates. Then there was a discussion about password-dependent and independent memory accesses. So based on the kind of memory access, your scheme might be vulnerable to cache timing attacks, for example. Then, of course, the FPGA, ASIC, and GPU resistance was a big topic. Then Kovatovich and his colleagues came up with attacks on iterated compression function, which highly depends on the hash function you deploy as a basic primitive in your password hashing scheme. Then there was a neat delegation feature of the password scheme Marqua, which was based on asymmetric cryptography. And then 2 major properties called client-independent update, which allows to update the password hash without any interaction of the client. So you do not have to type the password itself, which is quite neat if you have some inactive user accounts. Like last year we found, or some years ago we found out that Facebook has like 70% of their accounts are inactive. So you can still update the passwords without interaction. And then, which was also quite nice, is server relief, where you can just the main effort of computing the password hash is shifted to the client. So like if you're a Facebook, so you have like 1 million logins per day or per hour or whatever, then you do not have to do the main memory and time effort, but you can just shift it to the client. And then, yeah, the question why we're looking at Catena, first of all, yeah, it's our scheme, and it was published 1 year before the password hashing competition, and it has some quite new ideas, or brought up some new ideas. Like it was the first really flexible memory demanding password scheme. So there was bcrypt before, there was YesScript before, but they were not quite flexible. And we have a lot of flexibility. We can replace or instantiate our underlying primitives with certain kinds of other primitives to protect against certain adversaries. Then it was the first password hashing scheme which implicitly supports client-independent updates and server relief. And it's based on a text we found on script. It also provided cache timing resistance. But today I will present one example where we also have some kind of vulnerability against cache timing resistance, but in the favor of a sequential memory hardness which delivers a high time memory trade-off, or which thwarts adversaries using these kind of trade-offs. Yeah, the flexibility of Catena is basically given by, it looks like a lot of parameters, but once you understand them it becomes quite easy to build your own variant or instance. So first of all, we have two kinds of hash functions, where H is a cryptographic hash function always. It cannot or should not be a reduced one, because then we cannot guarantee the security we want to have. And we have a reduced hash function H prime, which can be deployed on certain positions to provide a better performance. Then we have a certain kind of memory hard functions F. And yeah, this is just 5 different graph instances which I will introduce briefly later. Then we have the time and memory cost parameter. So actually lambda is the depth of the graph itself, and G is you can say that the width, and 2 to the G is the maximum number of memory you will use if you are a legal user. And then I will present today two extensions to our core function. So our core function is actually called flap, because every variant is like a fly. And then flap was the logical choice for a name. I will present two extensions. One is gamma, which deploys a password-independent memory access pattern, but provides some neat resistance against ASICs. And I provide the second I will introduce the second extension, which is called phi, and this is like it writes the memory like in script, so we have some sequential memory hardness, which is really, really good against trade-off or low memory attacks. Okay, so based on the PHC and based on the discussions, we have some certain security requirements we are looking at. The first, or the common security requirements were like, okay, we have some pre-image resistance, which is always required for password hashing, obviously. Then we want to have some resistance against low memory attacks, because we're looking at memory demanding password hashing schemes. And if you have an adversary which is allowed to use low memory and still get the password hash in an adequate time, it does not really make sense. So we want to have some resistance against these low memory attacks. And of course, FPGA ASIC GPU resistance, which naturally comes with a high memory usage. And especially if you look at ASICs, then we want to have some randomness in there, because, for obvious reasons, Okay, then we have some application-dependent security goals, which means, do I consider adversaries which are able to actually look at the memory I use for password hashing? So we have two kinds of attacks. The first is the garbage collector attacks, and second is cache timing attacks. And we have, for key derivation, the biggest goal is like random oracle security, which is not required for password hashing, but which is required for key derivation, because for key derivation you always want to have randomness in your keys, because else a lot of proofs just fall apart. Okay, now we come to Catena framework. Actually it looks like this. So first of all, we have this, nice. So we have this tweak here. So we have 3 inputs. So the tweak, the password, and the salt. And the tweak contains everything you can think of. It's like user ID, server ID, IP, whatever, as you want. So it's like making the password hash as unique as possible. So you have, for the same user and the same password, you will get different hashes on different systems, even if they use the same salt. The salt is always required for like rainbow table attacks, or it's a common input for password hashing schemes. And of course the password. Then we put these inputs into a cryptographic hash function. So this always these two always have to be cryptographic hash functions and not a reduced one, because else we cannot guarantee pre-image security. And then also one important part is after you hash these three inputs, you can throw the password away. You should overwrite it in memory, because else you will get vulnerable to weak garbage collector attacks, where we just say, okay, you can look at the memory during the computation of the password hash, and you will find a password, or you find a value which is efficiently derived from the password. So this actually is also one security part against weak garbage collector attacks, because not only the password itself has to be overwritten, but if you gain a value which is significantly fast derived from the password and you can fetch it from memory, then you can, of course, test password candidates much faster and do not have to do all the thing here. This is why we deploy the small flap function here, which just overrides the memory in a fast way. This is why this is smaller. Then we have the big one. This is actually this loop. It's the core of the loop, so it can be called multiple times, but in our recommendations we have the same G, which is actually called garlic. So this determines the memory used, and we always set it to one value, so this loop is actually called once in our recommendations. And then you call the basic, or the core of Catena. And I will say something about in a minute. So this is actually based, it's a memory hard, so we require it to be memory hard, which means it provides some resistance against high memory trade-off attacks. And this is always, in our instance, it's always given by a graph-based structure. But I will explain it soon. And yeah, at the end there's a last call to a cryptographic hash function G before the output is generated, and this hash function actually leads to pre-image resistance for our scheme. Because if you cannot invert from X to here, you cannot, of course, also not invert from X to the password, so actually this hash function call here determines the pre-image security. And a second one, if you look at the structure, you can just draw a line here, and everything above this line is done by the client, for example, and then this X is sent to the server, and the server just has to hash this value, and then we have like a server relief. Okay, and yeah, at the end we can have some truncation, but if you truncate to like 32 bits or 16 bits, then of course it's not that secure anymore. So usually the output here is given with 512 bits. So if you just want to store 128 bit or something like this, then it's still secure and it works, but too much truncation is not good, obviously. Then to the curve Catena, we have, as I said, so this is the big part here. This looks like a graph-based structure where we process the output of the former call to flap. And then we have some sequential layer here. Okay, sorry, one thing. This hash function actually uses the cryptographic hash function H and produces state words of arbitrary size, because we use different hash functions. So the lines here, these small arrows, are always hash function calls, and the dots are the vertices are state values. So we have 2 to the G state values here. And these are produced by calling the hash function. And if you want to have a high performance, then except for this one and always the first one, all values can be computed with the reduced version of the hash function. So just for performance issues. Okay, the core actually, we require this one, the core, to have a password independent memory access pattern, because then cache timing attacks are not an issue for us. It's always graph-based, and we will see which instances we considered for this one. Okay. Yeah. Actually, this arrow is quite a bit misleading, because we always use 2 inputs. Sorry for this. This was the initial variant, and we updated it to use the 2 formally computed values, because then some certain trade-off attacks introduced by Kovatovich last year were not possible anymore or required a lot more memory. And then at the end, the last value of this graph, or the last computed value, is actually the output of this call to flap. Okay. Now to the extensions. The first one is called gamma, and we always use gamma in front of the function f. So this is just another, we call it layer, so it's just another operation on the internal state. It updates the internal state, but not the full one, because this would be too bad regarding to performance issues. So we say, okay, we want to have 2 to the 3g divided by 4 randomly chosen state words which are updated. And randomly chosen in this case means the input gamma is a public input. So these chosen state words depend, or can, for example, depend on the salt. We do not want to have dependencies on the password here, because we call it in front of f, and if you have some cache timing problems here, you will reduce if you launch a cache timing attack, you reduce the effort for computing a password hash, or just for looking at the memory accesses in this part, so you can reduce the effort for testing a password candidate significantly. So at the first place, or in the beginning, we always want to have some password independent but random memory words overwritten. In this case, we use the salt. And of course, this always supports some, or provides some resistance against ASICs, because, as I already said, random memory accesses always destroy ASICs. You actually can compute this one, because this is a deterministic graph-based structure. You can actually compute this, not on an ASIC, then copy everything to the ASIC, compute this one, and then copy him back or something like this. But we think this becomes is not really reasonable. The second extension is called phi, and we use secret-dependent memory accesses, which means in this case it's basically depend on the password, but not on the password itself, of course, but on the last state word of this graph structure. So of course all these values depend on the password, because it's the input to our scheme. And then in our recommendation, we overwrite all words here, so in a sequential manner, and the input words here are given randomly. So actually we have a state of 2 to the g values here, and to compute this one, we choose the preprocessor, which is this one, and then some randomly chosen value from here. And the choice of the value depends. The first choice depends on the least significant g bits of this state word, and so on. So actually, this one is computed by its predecessor, and the second input is determined by the least significant g bits of this one. So this actually behaves like a script, where we have a state of 2 to the g values, and all the inputs for the next value for the computation is chosen randomly based on already computed state words. And this provides sequential memory hardness, which means if you have a parallel setting, you cannot reduce the memory for simple password computations, for single password computations. Okay, I think I have to speed up a bit, so I will just fly over the graph structures. There's not much to explain it anyway. So this is we have this 2 to the g values. In this case, g is 3. And the first idea of our first instance of Catena was using the bit reversal permutation, where just the bits or the values are given as a bit representation, and then they are just inverted in their order, and then the output was given. So actually we have always 2 inputs to compute the next one. The second one is a shifted bit reversal, where we just add some value c, and in this case, in the bit reversal, you can see it's like quite symmetric. And this was exploited by an attack by Kovatovich, so we searched for another variant, or another graph. So this looks like not as symmetric anymore, but it's based on the bit reversal permutation, and that's why it didn't deliver any good results against the attacks we considered. So we came up, or we searched for new graphs, and then we came, or actually Ben Harris, I think, came up on the PhD mailing list with the gray reverse graph. And this protects quite well against the precomputations attack, which was introduced by Kovačević. So there are two variants with with x2 and x3, and then of course the graph structure changes. And this was also one basic instance we had to look at. It looks quite complicated. This is actually 2 times the fast Fourier transformation with one omitted row in the middle, and this provides lambda memory hardness, which was proven by Langauer and Tayan. But I will skip the details. So in comparison, we just found out that against the attacks we considered, the gray reverse graph was the best choice. So it has the highest penalty, which means the additional effort an adversary has to do if it has less memory available. Okay, just for comparison. So we have some really fast variant, some tunable fast variant, which does not protect very well against the attacks. Then some quite fast variant, which protects good, and the best protection is given by the most complicated variant, which is of course also quite slow. Okay, this is just a comparison of the hash functions we use, but I will skip this. Okay, here you can just see, okay, the fastest version is the CF is the compression function actually used in Argon with the Lyra function used inside. But I will skip to the new recommendations. I hope I have some 2 minutes, maybe. I will skip over this fast because this is actually our contribution. Here you can see one thing is we put everything together. We had our ways to build instances, and then we put 4 different instances where we have so we use both extensions, but a fast graph traversal operation. So we have some need protection against ASIC GPUs, are still fast, and have some multiplication hardening based on the Blumka compression function, and we have, of course, sequential memory hardness because of this phi layer. The second one is the fastest one with throughput about 1 gigabyte per second. This allows for garbage collector attacks if we have only 1 layer of this one. If we have 2 layers, then it protects quite well. So this is the fast variant of Catena. Then we have some trade-off resistant variant, which uses the complex graph and the sequential memory hard extension. So this is the maximum resistance against trade-offs, but while still providing reasonable performance. And then we have this hybrid approach, which quite well protects against ASICs using the gamma layer, and so also has good resistance against trade-off attacks while still gaining or providing some reasonable performance. And so this is just a fast comparison of the 4. And now I come to conclusion. Okay, sorry for the high speed. So what we have shown, okay, Catena is a quite flexible framework. So we can replace a lot of the underlying primitives and the underlying schemes by providing certain security goals. We had a look at different instantiations of H prime and the graph-based instantiations, and we introduced 2 extensions to our scheme for certain security reasons. Then at the end we had 4 new instances for password hashing, and we can use the same instances but with bigger graphs and replacing the reduced hash function by the cryptographic hash functions. Then we can use these instances for key derivation. And the future work would be, okay, looking at different graph instances where we can say we want to have a lambda memory hard graph instance but with a constant depth. So the most complex graph which I've shown grows in the depth if it also grows in the width. So but we want to have but we want to have a constant size graph, at least for the depth. Okay, so the last slide is actually questions. Yeah. Okay, so thank you.